Hey, welcome to the Zig for the Uninitiated. My name is Tyler, and let's get started. Today we're going to talk a bit about going beyond the page allocator. And so if you haven't watched my video from my previous video about the page allocator, I highly recommend going and watching it because it's going to be very foundational to today's video. So in that last video, when we talked about the page allocator, we kind of talked about what it does. And what it does is it goes to the operating system and it asks for the minimal amount of memory that the OS will give. And that's called a page. And you know, the OS is not going to give you 1 byte or 2 bytes or 8 bytes. It's going to give you a whole page worth, which on a lot of systems is going to be 4,096 bytes, 4 kilobytes. So with the page allocator only giving us, this amount of space, there's a problem is that if we only need 1 byte, we're wasting 4,095 bytes of space. And then if we need another one and we go back to the page allocator, we're going to have a lot of wasted space. Would it be nice if we could just manage that memory ourselves, right? And say, hey, give us all the whole page and then we'll divvy it out. And that's what the other allocators in the Zig standard library do, is that they take upon themselves to, with a little bit of overhead, manage that memory. So that the page allocator kind of demonstrates one problem that we have when we're doing with memory allocations, which is waste. A lot of times this is called internal fragmentation, but I'm going to call it waste so that we don't get it mixed up with fragmentation, what is often called external fragmentation. And these are two problems that all allocators have to deal with. So like I said, with the page allocator, the problem is, say we had, this whole memory region, and we only needed 256 bytes from it, right? So we take up this area, let's say each of these blocks is 256 bytes. We've used this one, and these other 3,000 and so bytes are just wasted. We can't use it. What other allocators seek to do is to manage that memory. Say, you know what? We know that there's 256 bytes used here. We can use these other 3,000 bytes for other things. Now that causes and is related to this other problem of fragmentation. And I'm going to explain what fragmentation is here. So when you have fragmentation, right? When we have fragmentation, so what fragmentation is let's say we have this similar situation. We have a whole page of memory here, and we need 16 256 byte objects allocated. So we're going to allocate one here, and one here, and one here, and one here, and 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 so on until we are done. And then later we go through, we have all the pointers to those stored in some array, and as it goes through this array, we pass it through some filter, and the filter ends up freeing all of these ones because we decide we don't need every other allocation back. Well, now we have a problem here because we only are using half of our space, 250 or 2048, right? Half of it's free and half of it's used. But we can't allocate anything larger than 256 bytes because there's no contiguous space that would fit that. Each of these are only 256 bytes large. So if we wanted to allocate something that was 257 bytes, we would have to go back to the operating system and ask for more, or crash if there was no more memory left, right? Even though we have 2,000 bytes left, 2 kilobytes of free space here. I know 2 kilobytes, I'm making it sound like a lot, but for that, if we were on a really small memory system, or we were just trying to really limit ourselves, or for any reason, we're wasting half our space here. So these are both related to waste. This is waste because we're just not using it. This is waste because we can't get at it. The memory is fragmented. And so that is the goal of every allocator, is to I don't want to say eliminate, I don't want to say minimize, because none of them do that. That's what's really exciting about working with allocators, is that there is no silver bullet. There is no single solution that's optimal. If there was an optimal solution, then the whole point of Zig having this whole allocator interface would be ridiculous, because who would care? We'd just always use the optimal one. But there isn't. There's thousands of different options and different ways you can allocate memory that help resolve this problem of waste, fragmentation, or in further discussions on performance. And so sometimes you might come into coding in Zig that you find that your memory usage pattern isn't one that works for the allocator you're working with. And so that's when you will want to go reach out for other allocators, or maybe even craft one yourself that is perfectly fitted for your memory use pattern. Now, with that said, let's talk about the general purpose allocator, which the general purpose allocator's purpose is to fit a general usage pattern. And when I say general usage pattern, it doesn't mean that most people, that this works 99% of the time or 90 or 80% of the time. No, it means general in the sense of, you know what, we don't know what your usage pattern is. So we're going to have to generally think that your pattern could be completely random. You could be allocating something here, a huge thing here and a small thing next, and then another big thing, and then another small thing, and then 100 of these things. Your pattern is there's no assumptions made about your allocation pattern and your freeing pattern, what order you're going to free things. And the general purpose allocator is designed to work for that situation. And so I'm going to go into this because I want to explain the why or how the general purpose allocator works and a bit of its internals, which I know might be going beyond a bit the Zig for the uninitiated level of things, but I think it's important because when you understand how the general purpose allocator works, you can understand whether your usage pattern really is good for it or not. Okay, so here I've got this little chart because the way I drew memory out here is a bit of a lie. The general purpose allocator does not see memory like this in a way. It sees memory like this. And the way I am showing you here is based off of an assumption that we have a page size of 4,096 bytes, which is fairly common. It's what you'll get on Linux, you'll get on most architectures, is 4,096 bytes. So that's what I'm going to use. The way the general purpose allocator works is that it divides memory up into different bucket classes. And in this case, it's going to be 12 bucket classes. It's whatever log base 2 of your page size is. So log base 2 is 12. Log base 2 of 4096 is 12. And it's going to divide up the memory space, or it's going to divide up your allocations amongst these bucket classes. And so you can see here I have it. We have 1, 2, 3, 4. We've got all 12 buckets. You have a bucket class for 1 byte allocations, a bucket class for 2 byte allocations, a bucket class for 3 to 4 byte allocations, a bucket class for 7 to 8 bytes, and then for 9 to 16, and so on and so forth. So each bucket class is for allocations that are up to its class size, which then means that each of those can be slotted because each of these receive their own page in memory. So if you allocate 1 byte on the heap, you're going to get a whole page, but you'll be able to use the rest of that page. But that rest of that page is only going to be used for 1 byte allocations. And so you have what is essentially 4,096 slots to be used there. Similarly, if we were allocating 16 byte objects, you'd have 256 slots in that page of memory. And so that's how the general purpose allocator is kind of combating the fragmentation aspect, because it is accepting a little bit of waste, because at worst case scenario, you're going to be wasting a little less than half your memory in the page, but you'll always know that every slot is used. And this goes a little too deep for the video, but by using those slots, it makes it a lot easier for the allocator, which has its own own overhead memory that it's using. It makes it a lot easier for it to keep track of what bytes are in use or what slots are free, which ones are not. That's at a very basic level how the allocator works. You say, hey, I want something. It goes and finds an empty slot in that whatever the bucket class it fits in, and it gives you a pointer to the start of that slot. And there you go. You've got your memory there. Now, if you have things that are larger than 2048 bytes or larger than half your page size, that is what gets called a large allocation. All these are called small allocations, but larger than half the page size is considered a large allocation, and the GPA handles those individually and a hash table called the large allocation table. So yeah, in short, that's how the general purpose allocator works. Now, I think what's probably more interesting to people is how to use the general purpose allocator. So I've written a little script here that I've used to help both understand how it works and show how to use it. So the first thing when you use a general purpose allocator is to understand where you call it from. So you're going to find the general purpose allocator under standard.heap, and the general purpose allocator function is a generic function, which means it's a function in Zig that returns a type. And so what you do is you give it some configuration and you'll get an actually what is a configured version of the general purpose allocator type. And I'll explain a little more into that later, but I want to go into the configuration properties because the last time I talked about this, I kind of brushed over it. A lot of times all you're going to want to do is just use the default config properties. But what makes Zig's general purpose allocator very nice is that it has built into it a lot of debugging tools, a lot of tools to help you debug memory issues. There are several different configuration options, and I want to go through them. So these ones I've blanked out because I'm not going to use them, and so I'm just going to take the defaults, but I did want to talk about them. First is stack trace frames. So one of the debugging things that you get from the general purpose allocator is that you get, it will keep a stack frame trace of every allocation and every free. And that's used in debug mode. I want to make that certain. In debug mode, in release mode, in release safe, in release fast, and release small, you do not get stack trace frames. This is in debug mode only. And you'll get 10 stack trace frames if it's in a testing context. You'll get 6 in a non-testing context. If you don't like that and you want to do release fast, but you also want to waste a ton of memory keeping track of the stack frames of every allocation, then you can set this yourself. But usually I think it's pretty good to leave it at the default. Usually don't need more than 6. If you find that you do when you're trying to debug something, it's nice to go in and do that. Enable memory limit. This is a more advanced thing. Basically, if you have this set to true, you can then impose a limit on the amount of memory total, like overall, that the GPA is going to use for allocations. I don't believe that applies overall to the overhead that the GPA uses to manage all your memory. It's just to the allocations that you request. So say you said, I only want to use 4 gigabytes of memory here, then the GPA will you can say set the memory limit to true, and then you can, when you create the instance of your GPA, you will have to set what that memory limit is. Safety. This is just this is used to keep track of runtime safety, and it's a flag that allows some other options. Really, I just keep it to the default. I don't really see a reason to change that at all. Thread safe. This is based off of whether or not you're building single threaded or not. Once again, this comes from built-in, which then means it comes from the compiler. The compiler is going to know whether you're building single threaded or not. No real reason to change it. It's going to be true if you're building it'll be true if you're building in a non-thread safe environment. Where it comes into importance is, or rather, if you're building in a threaded environment, it'll be true. Is that if it's true, you will need to set a mutex type so that that the allocator itself can be thread safe. If you're building a single threaded, you don't even need to worry about that. You can just leave mutex type null, which is the default. Okay, these next three are useful, really useful for debugging. We're gonna start with verbose log. Verbose log just logs a message about what's been allocated every time you do an allocation. It logs the size of the allocation and the location of the allocation. And it also logs it whenever you free. It's nice, it's really wordy, but it's nice to have if you're really trying to struggle to find where that seg fault's happening or where you're leaking memory or any other reason. Never unmap, retain metadata. These two go hand in hand. I don't remember which one it is. One of them doesn't make any sense to do without the other. And I think it's never unmap. Never unmap intentionally leaks memory. And it really only makes sense in the case of retain metadata. Or I might have that backwards. By the way, they make sense to go hand in hand because when you have them on, it allows extra debugging ability to make sure that you can keep track. Because never unmap, when you free memory, if never unmap is true, it never actually frees the memory. It keeps it retained. And retain metadata retains metadata about allocations so that even if you free them, you can then keep track of where the data actually went happen, and it can help you track down, use double freeze and just memory errors, I think. Anyways, I've turned them on here just to see how they work and what they do. A practice I've started doing with the GPA in particular here is whenever you create it, and this is, I think, probably a good practice in general with Zig's generic function types, is that when you do them, when you use them, is to alias those function types. You don't have to do this, right? I could use this and then create my allocator, right? I could do .init, right? And I could get the allocator there that way, and I'll show you what that means in just a second. But I like to create this because then I can reference the type. I can reference this configured type, because what this GPA is this specifically configured version of the general purpose allocator rather than a general purpose allocator. And that gets into how generics work in Zig. And that's beyond the scope of this video. And maybe I'll do another video about it later, but I like it. I'll show you where it makes sense later. Jumping down to line 25 down here, you can see what I've done is created my instance of the GPA. And I do that using this 0.14 syntax, which is you just use this .init class. If you jump there, you can see this is how it's created. If I wanted to change these things, I could do it differently. No, if you're still on 0.13, this is broken. This will not work. This is the way that Zig is going to declaring default or initializer, default initializers. This is the way Zig was in 0.13. So if you're on 0.13, you'll need to use it this way. And technically, this is still legal in 0.14, but it won't be forever. Once you declare your general purpose allocator, it's a good idea to immediately defer if you're in the right context for it, but to defer and defer these two function calls, detect leaks and dinit, and you want to do them in this order, because if you do them in the opposite order, the dinit is going to deinitialize all your data before you can detect the leaks, which then ends up the detect leaks tries to read uninitialized data and it causes a problem. So detect leaks first, then deinitialize. This is nice for debugging because if you've leaked data, it will notify you. Okay, and then like all other allocators, once we have our instance of an allocator, we really just want the interface, and so we use the allocator function to get the interface, and that's what we'll be using to make our allocations against. So that's it for talking about the general purpose allocator. I hope this was informative and interesting. If this was too much, please let me know in the comments. If you said, hey, Tyler, that was too complicated, I can come back and we can make a less complicated one. I wanted to go over the internals because I think understanding allocators in Zig is about understanding the usage pattern the allocator is made for. And to do that, you kind of need to get into the internals of the allocator. Next up, barring that if I need to revisit this, I'm really now planning to get into the arena allocator because I think we have everything set up to go over the arena. And once we've done the arena allocator, I think that'll be enough on allocation. We might take tact we might turn and start visiting other interesting paths in Zig. So I'd love to hear what you guys would like to learn about. I've already gotten a few comments on that, and I'm planning some ideas around those. But happy coding.